Hi, welcome to another edition of Linear Algebra. Today we are going to take a look at several problems related to dot product. Let's see how many problems we can take a look at today. So, of course, some basic problems are related to finding the length or finding the angle of between vectors and such. I believe you can do all of these things easily, and we have done several examples of them. You can always consult your textbooks or videos on WebAssign itself for quick review of these items. Let's go take a look at some problems that are a bit more advanced. Here problem 48, 49 and so on. So problem 48 here says I have some vector, call it u. This one has components 2, 3, and I have another vector whose components given by a parameter, in this case k. One of them is k plus 1, the other one is k minus 1, and the question is find values of k for which u and v are orthogonal. Okay, this word might not be familiar to you. Orthogonal simply means perpendicular, just a fancier way of saying. Also, we use the word normal. So, normal, perpendicular, orthogonal, or sometimes we have this abbreviation, just perpendicular to each other. Well, if you put different values of k, some of them, you always get a vector v, but it's not going to be perpendicular to vector u. So what's the easy way of doing this? You can do this in graphically, but easiest way is to remember that u dot v was equal to length of u times length of v times cosine of theta. So if the two vectors are perpendicular to each other, well, then cosine of 90 degrees will be 0. This theta in that case is 90 degrees, and as a result u dot v is going to be 0. And also in reverse, if u dot v is 0, then the vectors perpendicular to each other if they have an extension. So we calculate u dot v simply. So what is u dot v? We learned first component times the first component, and the second component times the second component added to each other. And what we expect is for the dot product to be 0. All we have to do is a simple algebraic equation to solve now, like 2k plus 2 plus 3k minus 3 has to be 0. So 5k minus 1 has to be 0, and k has to be 1/5, and that is the k for which this property is going to emerge. You can always verify your solution to make sure you have not made some algebra mistake here. So we had one vector 2, 3, and the other one, well, k turned out to be, it has to be 1/5, and then the other one is 1/5 minus 1. So let's simplify this thing. It becomes 6/5, and this is minus 4/5. It's always a good idea to simplify your fractions as much as you can. So I can factor, for example, 2/3 out, and then that becomes 3 minus 2. Well, obviously if I multiply 2, 3 with 3 minus 2, I'm going to get a 0, and that means that the two vectors are perpendicular to each other. Okay, several other problems like this show up in the text. If you do them, sometimes you might come across equations that are a bit more complicated than that. It could be quadratic, cubic and such, and then you just use your knowledge from college algebra to solve those equations, and they're all done. Next problem, problem 50. It says suppose I have a vector u. Again, this is 3 1, and then the question is describe all vectors v whose components are completely left open, so x and y, so that u and v are orthogonal. So u is perpendicular to v. Well, same as before, we do u dot v, so that is 3x plus y, or 1y if you wish, so 1y. That has to be equal to 0. So long as you have an x and a y that satisfy this equation, you're right, all set. Well, let's reduce the number of variables that we have in front of us right now. You're saying find an x and a y that solve this equation. Well, let's go ahead and solve it. You have a choice of solving y in terms of x or x in terms of y. It's your choice. So here let's say y has to be equal to minus 3x. In that case, so y has to be minus 3x for this v to be perpendicular to that. So we are go ahead and rewrite v one more time. Well, x is x and y is minus 3x. Again, we said you can factor an x out. So what kind of vector v's are perpendicular to vector u? So long as you have vector v as any multiple of vector 1 minus 3. So this is 3 1. Notice the other one, the two components are flipped. In one of them, the sign is also flipped. So the location of first and second components are exchanged, and one of them has to be negative of what it was originally. It doesn't matter which one, just one of them. Then this vector will be perpendicular to that. Again, it's very easy to check. If you have 3 1 and you multiply dot it with any multiple of 1 minus 3, well, the multiplier x just stays out. 3 times 1 and then minus 1 times 3, well, they cancel each other and you do get 0 at all time. So this is a description of all the vectors v. Any multiple of 1 minus 3 will do. Might be instructive to just have a little graph that tells us what is going on. So u was 3 1, so suppose 1 2 3 and 1, so that is my u. We want to describe all the vectors that are perpendicular to this. Well, in geometry that would have been easy. You just draw make sure my drawing is good. So you draw a line. This is the line that's perpendicular to u. Well, we want to characterize it by a vector. So we say if this was vector 3 1, look at the vector 1 minus 3. 1 minus 3. So let's color that. Look at the green vector v multiplied by any number. So x is any number. Like if you want to double this, triple it, or multiply by minus 1, minus 2, or any fractional number, whatever you get, that's going to be an acceptable description of vector v, and that is the set of all vectors that are perpendicular to u are going to sit on this blue line, and that is the description. Of course, if the problem comes up in WebAssign, you look at how you're supposed to enter the final answer, and you do accordingly. Okay, another interesting problem. related to, say, problem 62 is the following. If I have a parallelogram, so suppose I have a parallelogram, but this looks like a bit like a rhombus, so let's make it general looking. Well, there are some length associated with these sides. Suppose this is of length A, this is length B, and of course this is B again, and this is going to be A again. And then there are two diagonals. Let's call one of them, say, diagonal C, and the other one diagonal D. Version of that problem says show that in any parallelogram sum of the square of the sides, so a squared plus b squared plus a squared again plus again b squared, is equal to sum of the square of the diagonals. So show that in any parallelogram sum of square of sides is equal to sum of square of diagonals. There are two diagonals, and well, of course any reasonable person is going to write this as 2a squared plus b squared is equal to c squared plus d squared. Okay, so this is kind of like those proof problems that we had before. General properties given, and we are expected to show that for all possible cases, for all parallelograms, there is no number in sight, no particular formula to use and such. So we have to be a bit creative here to come up with some approach to this. Of course, the problem could have been given to you in pretty much any math class. It could have been college algebra, pre-calculus, calculus 1, and so on. Looks like a lot of Pythagorean theorem or distance formula and such. Well, we are doing linear algebra. This is a section on dot products, and we might as well try to use that approach. So let's suppose I have a vector showing this side A and another vector showing the other side B. So little a is the length of A, little b is the length of B, and then you can make your parallelogram by just copying these two vectors. And last time we said that this diagonal that shares the same origin with A and B is A plus B, and the other one, depending on which way you want to go, from B to A or A to B, you have one of two formulas to use. Let me draw out some other color. So suppose we go this way. If you are going this way, then you have to go minus B plus A, so that this one would be A minus B. So the problem is reduced to the following, that twice the length of A squared and the length of B squared is equal to, well, the diagonals is A plus B squared and then A minus B squared. So given essentially problem is reduced to the following: given any two vectors A and B, show that this is true. Well, the easiest thing to do is start from right hand side and clean it up. So if I have A plus B squared, what did we say that is? Well, you remember any vector squared same as that vector dotted with itself. So this is going to be A plus B dotted with A plus B, which we learn how to simplify. A dot A, just basic foiling, in twice the cross product. It's just that you have to remember these are dot products. So a dot a is the length of a squared, this is length of b squared, and this is the dot product. Well, same thing with the subtraction. A minus b squared, exact same as here. The only thing that happens is that becomes minus 2a dot b. And of course, if you add these two, a plus b squared plus a minus b squared, the magic that happens is that this plus and minus cancel out, and we double up on this portion, becomes twice a squared plus b squared. So a nice interpretation. Sum of squares of the sides of a parallelogram is equal to sum of squares of the diagonals of that parallelogram. So that was another application of dot product. Let's go to an interesting problem that has many solutions, which is how to find the area of a triangle. How to find the area of a triangle. Well, of course, this is something you have seen since elementary school, and it shows up in so many versions. And here are a few other versions using linear algebra. A couple of these things are mentioned in some of the homework problems that you're going to solve, and let me do it even in a third way, different from what the textbook is recommending that you do. So these problems here show up under problems 46, 47. So two approaches are mentioned there. Like, make sure you study that. Of course, we are in section 1, 2. So you follow the procedure that is mentioned there. And here's still another approach, which is the following. Well, let's go back to very beginning. You learned this base times height divided by 2. Well, where does that formula come from? We actually talked about this thing in the previous lecture. So if I have triangle like this, it has a base, it has a height, and base times height over 2 is the area. Question is why? If you understand these things very well, then all these variety of approaches that come to us, we'll have a much easier time maneuvering between them, and they don't look like coming out of thin air to us all that much. So let's go ahead, color this. Well, we said last time, if you have a right triangle, so if I have a right triangle like this, let's call this thing B. This is the right base maybe, and this is the height. Well, if you complete this thing, it becomes a rectangle, and the area of this rectangle is this base times height, and therefore the area of this half of it obviously is going to be 1/2 of base times its height. And of course, you can make another one of these things from the left portion. So for the left portion, you can do exact same thing. So in this case, you have B, the portion of the base on the left. So we might describe it as BL, meaning the base on the left. And then you do this one in the same way. So 1/2 of B on the left times height. If you add them, you get the total area. So when you add them, you can factor your half, you can factor your h, and have base on the left and base on the right in parentheses, and all of this thing together is, of course, is just your overall base. So half base times height, or you can make a parallelogram and make a discussion just like that. Okay. So in elementary school, they just tell you what is base and what is height, and all that you have to do is remember that, and then you multiply, and then you're all done. Now, what if what if they haven't given you any of these things? For example, in the problems here, they might give you the coordinates. So the coordinate of this point might be given x1, y1, z1, x2, y2, z2, or x3, y3, z3. The coordinates might be given, and then the question is, well, how do you find the area then? Well, you might say, well, find the base and the height. Well, those are going to be steps that are going to take a bit of time. And the question is, can we do this thing cleanly without getting bogged down with a lot of calculations? So the two methods mentioned in the text, you follow them. And here's another one. First of all, well, find this vector, similar to the approach to taking in the text. Let's call this thing A. Find this vector, let's give that a name B. How do you find these vectors? Simply subtract the beginning from the end and subtract this from that one. So that gives you your A and B. So let me make this clear. So A will be x2 minus x1, y2 minus y1, z2 minus z1, and B will be same, x3 minus x1, y3 minus y1, z3 minus z1. So that tells us what the A and B are. Next, well, the question is, how do you get your height? Well, height, let's go ahead and focus in this blue triangle. Let's call this angle theta. So if I have this triangle here with the angle theta here, and this is the hypotenuse, which is the length of B, then the height is going to be the length of B times the sine of this angle. Is that right? Basic trigonometry. The opposite is equal to hypotenuse times the sine of the angle. So that's my height, and the base is going to be the length of A. So the area, one formula for the area becomes, you have the base is A, the height is this, and then we have a factor of 1/2. So area of a triangle follows this. Okay, so far so good. So this is one of the formulas. This is also given in the text. Area of a triangle, 1/2 the length of one side, another side, and sine of the angle between the two sides. So now question is delegated to, well, how do you find this sine? These two lengths are the length of these two vectors. That would be easy. How about the sine? Well, we remember sine is going to be, well, this angle sine is always positive, and from trigonometry we remember the sine of theta is equal to 1 minus cosine square of theta. Is that right? Pythagorean theorem there. Wait, now you're saying, well, how about cosine of theta? Where do I get the cosine of theta from? It looks like we're jumping from a frying pan to fire and not resolving this problem. But remember, we did have a formula for cosine of theta. That was A dot B divided by length of A times length of B. Okay, so the dot, here's the application of the dot product. That gives you the cosine theta. So I put it here. So I have a formula for my area. It's going to be 1/2 length of A, length of B, times radical, 1 minus, that is A dot B over length of A, length of B. That's a cosine. The whole thing has to be squared. We might as well clean this up a little bit so that in application we'll have easier time. So I'll have 1/2, I leave it outside. A, B, I take it inside radical in the hope of cleaning this up. Remember, if you take a number from, a positive number from outside of a radical to inside, of course you have to square it. So this, when it goes inside, becomes A squared, B squared, and the A squared B squared is going to cancel the A squared B squared in the denominator here, and all that's going to be left is A dot B squared. So here's a formula for the area of a triangle. It works in any dimension, and you can extract a lot of interesting little applications out of it. In 2-dimension, the formula becomes very simple. I encourage you to go ahead and try to simplify that and find out what the formula will be. So if we didn't have this in 3-dimension, we just had 2-dimension like x and y only, there is a nice simple formula. You might have seen it in your other classes that can also be extracted out of this. So in these two problems, 46, 47, if you just go ahead and calculate a and b in this style, and then you plug it here, and then you have your formula. Now I do want to insist that it's best that you try the problems yourself, do as much as you can, and then come and consult these problem solving sessions to see if your solution agrees with what we have done. And of course, if you have other questions, you can always bring it up. Many other questions in this section regarding projections and various inequalities. I hope you take a look at them and try to do as many of them as you can. Until next lecture, good luck and God bless.